All right, so this is going to be my redone version of the first exam 2 review session that we had on Thursday. For some reason, the recording I did got messed up, but I'm going to go over the same problems that I did in that session so that you guys can have the recording and the solution. So these are all problems out of the exam 2 review in you can find it in the modules on the engineering mechanics Canvas page. So we're going to start with problem 6, which is going to be a truss problem. It wants us to find the forces in members BC, EG, EF, and DF. And we can go ahead and label on the diagram which ones it wants us to find, just so we can see it a little bit easier. So right away we can identify that this one is by itself, and then we have 3 here, so it's probably safe to assume that we will take a cut through these, and that this one will be solved independently. The first thing you want to do for any kind of truss problem like this is we're going to need the reactions. We're going to need our HY. This is also going to have an HX. I apologize, I am writing with a mouse, so I will try to make it more legible than this. And we're going to have AY. There we go, that's better. So what we know about this structure is that the entire thing is symmetrical in all of its shapes. It's all even everywhere. It has the same shape on both sides, and we have the same applied forces all across it, even on both sides. We have 300 here, 300 here, and then 600 on all 3 middle points. So since the applied load is symmetrical and the shape is symmetrical, we know that our AY and our HY are both going to be half the sum of all of these, because the reactions are going to be half of the applied loads. So what we can do is we can just add all of these up, divide them by 2, and say that AY is equal to that, and HY is also equal to that. So we know that our AY and HY are going to be 300 plus 600 plus 600 plus 600 plus 300 divided by 2. So that means that HY or AY is going to be 1,200 pounds, and HY is going to be the same, 1,200 pounds. So we have our reactions. We can now go try to solve some of these members. So I recommend starting with the one by itself first, because we can easily take a look at this joint right here, and we can say, I think I can do this actually. We can say this, joint C. And we'll label this right here. This is C. This is going to be a cut. This is a cut. And there's our cut, where this is AC. This is CE. And we have BC. And this is it. We have no applied loads at C, so we can actually go ahead and say, I don't have the character for it on my keyboard, so I'm just going to write sum of F in Y direction. It's going to be equal to BC. And that's it. There's nothing else in this direction. So BC is equal to 0. That makes BC a 0 force member. So we can go ahead and write that this is 0. This blue. So that's our first answer. BC equal to 0. Then, oh no, okay, can't move any of that stuff. we can go ahead and take our next cut right here, like I showed before. And this is going to be cutting this entire structure right through this line. And we can either take the left side or the right side. We'll probably want to take the right side because it's much smaller than the left side. So I'm going to go ahead and show that. Where all of these have been cut. And we have H right there, G right there, and then we have F. And these are going to be our unknowns. We also are going to have, I'll make it a different color. £600 right here, and 300 pounds right here. Additionally, with HY and HX, I should have mentioned before, HX is equal to 0, because if you do some of the forces in the X direction about the entire diagram, this is the only external thing that would be in the equation. So it would just be some of the forces X direction equals 0 equals HX. Excuse me. So now that we've taken our cut and drawn our free body diagram, we can go ahead and take a moment. The goal taking a moment in any one of these problems is to eliminate as many of these unknown cut arrows as possible. So we can either take our moment at F and get rid of these two, or we can take our moment at E, at E and get rid of these two unknowns, because these ones would pass through EF and EG, or EF and EG will pass through E, while EF and DF will pass through F. So it's totally up to you whether you take the moment at F or E. Both are going to get rid of two of these unknowns. I'm going to go ahead and take the moment at F. So we'll say, just so I can keep the proper notation, sum of the moments at F equals to 0. So taking the moment about F, EF and DF are both going to go away. The 600 is going to go away. The 300 and HY, which is 1200. And then our unknown EG will all be accounted for in this. So if we say counterclockwise is positive about F, we're going to have minus EG times the distance from EG to F, which is going to be our 6 feet. Once again, counterclockwise about F, we're saying is positive, so we're going to have plus 1200 times the distance from H to F, so that's going to be 8 feet as H goes up like this. F is over here, that distance is 8 feet. And then counterclockwise about F, our last force is minus 300. Also times 8 feet. And that's all of our forces. If we take the moment about F, we can solve this and say that EG is equal to £1,200. And we get a positive answer, so this is going to be in tension. we get a positive answer, so our assumed direction of EG going to the left, aka tension, is correct. So then we could do either moment at E to find dF, or we could do some of the forces in the X and Y direction at the same time and do a systems of equations to solve this. So I will go ahead and show that we can do moment at E as well. So let's say clockwise positive moment about E. That's an E. It's equal to 0 is equal to, going around E in a clockwise motion, we're going to have the X and Y components of dF. So we'll have minus 4/5 dF. And sorry, I should say this 4/5 comes from the ratio of 8 feet to 6 feet being the horizontal and vertical components. So then you use Pythagorean theorem because it's a right triangle. You can get the distance of dF as 10. And then that just reduces to 4 in the horizontal and 5 in the diagonal direction. So that's where the 4/5 comes from. So this is our X component for dF. And we're going to have minus 3/5. Sorry, I should multiply by our distance from E to dF in the X direction. From E to dF in the X direction is going to be 6 feet. And then we'll have minus 3/5 dF. This distance from E to dF in the Y direction is going to be 8 feet, because dF in the Y direction is going to pass through F and go straight up and down. So that distance from E to F is going to be 8 feet. I'm also going to go ahead and write up here that we have EG equal to 1,200 pounds in tension. So back to our equation, we have the X and Y components of dF going around E in the clockwise direction. We're also going to have plus 600, even though it's going down, it's going to go with our assumed moment direction. As the moment comes around this side, it's going to go down and line up with 600. So we're going to have plus 600. Times the distance from E to F, again, it's going to be 8 feet. We also have 300 and 1,200, so we're going to have plus 300. Because as the moment goes around, 300 is going to line up and go with the moment. That distance is going to be 16 feet all the way out to H. And we're going to have minus 1,200, because 1,200 is going to go against the moment direction as the moment spins clockwise. Also times 16 feet, passing through H. So now that we have this equation for moment about E, we've accounted for all of our forces, and we only have one unknown, dF. So we can say that dF is equal to 1,000 pounds in compression. And that's just doing out this math and solving for dF. So dF is equal to 1,000 pounds compression. So that's 3 down. We've got BC. EG, and DF. We just need to solve for EF, and then that'll be it for this problem. So EF, here we can do some of the forces in the Y or X direction. Either one will, for this diagram, either one will allow us to solve for this. Using some of the forces in the Y direction, we'll have, actually some of the forces in the X direction would have slightly less to work with, because all three of these forces here are in Y direction, and in X direction we are only going to have these three. So sum of the forces in the X direction is going to be equal to 0. And equal to, we have our X component of DF, which we know is minus 4/5. Well, we know that, we know now that DF is in compression. So it actually goes like this. So if we're doing to the right is positive in the X direction, we know that DF is going to be to the right and down. So we're going to have plus 4/5 DF. And then EG, we know is 1,200 pounds going to the left because it's in tension. So minus EG. And then we will have assumed tension for EF, so we'll say minus, same ratio as DF, minus 4/5. That's a 5. EF. So we know what DF is, we know what EG is, EF is our only unknown, so therefore we can say EF is equal to, comes out to be 500 pounds in compression. We get a negative answer for EF, so we say that it's compression because we assumed tension for it. But in reality, it's compression. So EF equal to 500 pounds compression. And that is the last internal force that we needed, so we are done with this problem. And I'll go ahead and say it now. If anybody watching this after I post it has any questions on this problem or any of the following problems, feel free to shoot me an email and I can explain anything that's unclear. So I'll clear all drawings. We can move on to the second one. So this is problem 2 from the review. We have two weights, W1 equals 100 and W2 equals 200. This is, here we have W1 and here we have W2. They're suspended from this cable, and it wants us to find, what we're looking for is this distance and the tension in cable segment 2. So this tension value. So per usual, the first thing we're going to need to do is find our reactions. So if we want to go ahead and label this A, B, C, and D. We know that this is a cable fixed to a wall, so we're going to have an AY and an AX. Same thing on this side, we're going to have a DY and a DX. So we can take the moment on either side, either at A or at D, Taking the moment at A will give us dy. Taking the moment at D will give us ay. I'll go ahead and take the moment at D. And let's say it's a counterclockwise moment. Counterclockwise sum of the moments about D equal to 0. This is going to cross off both of our D reactions, and we're going to have plus W2, because W2 is going to be a force moving like this. W1 is also going to be a force moving like this. And as our moment moves around and gets onto this side, W1 and W2 are both going to be with the moment direction. So we're going to say plus 200 times the distance from D to our W2, which is 1 meter, plus 100 times the distance from D to our W1, which is 2 meters. And then finally, we're going to have minus AY because we're assuming AY goes up, times its distance of 3 meters. AX is going to not be included because as AX moves all the way to the right, it passes through D, and so it's not part of our moment equation. Therefore, we're done, and we can say, after solving this, that AY is equal to 133.3 newtons going up, because we get a positive answer, so our assumed direction of up is correct. Then doing some of the forces in the y direction, which will include our AY, our W1, our W2, and our DY. DY will be our only unknown. We can say DY is equal to 166.7 newtons, also going up, because we're going to have 133.3 minus 100 minus 200 plus dy. dy has to make up for the difference between ay and these two weights. So now that we have our reactions, we can we can actually start going into our cables. So the easiest way in this problem to get to our desired tension value in cable 2 is to just start with a cut around A, start with joint A, where we have our point A, our cut tension. This is going to be AB. We're going to have our AY value, and we'll have AX. AX is still unknown because if we take the sum of the forces in the X direction for this diagram, as you can see, this is a vertical, AY and DY are vertical loads, or vertical reactions, these are vertical loads. AX and DX are going to be our only things acting in the X direction, but they're not equal to 0, not for sure, because when we take our sum of the forces in the X direction equal to 0, equal to AX minus DX, we know that they're the same. That's going to add over. We're going to have, I'll write it out, we're going to have sum of the forces X direction equal to 0. Let's say positive is to the right, we're going to have AX minus DX. And that's it. That's everything in the X direction. So that's going to simplify to be AX equals DX. So we can't really do anything else with that other than know that these forces exist, or these reactions exist, I should say. So going back to our joint A, with AB being what we're looking for to move on and get tension in cable 2, we only have the options of doing some of the forces in Y or some of the forces in X. And since AX is unknown, we have to use AY as our known. So here we can do some of the forces in the Y direction equal to 0. It's going to be equal to AY, which is 133, And then we're going to have minus AB, because as we see, we assume tension for AB, so it's going down. And then we'll need the ratio. It's a 1 for horizontal and 1 for vertical, so that means this diagonal is square root 2. Because 1 squared plus 1 squared is 2, square root of that is square root 2, that's this distance. So our ratio is going to be 1 square root 2. And that's it. That's all of our forces in the y direction here. So AB is going to be equal to 188.5 newtons. And we get a positive answer, so our assumed tension is correct. We can then move to joint B. We can take this joint. We draw the cut. We have AB, which is known. We have W1, which is known. And we have T, I'm going to call it T2, because that's what the problem calls it. They call it, where is it? The tension in cable segment 2, so it's T2. So with AB being known and W1 being known, we only have to find T2. Now we could do this, we could do this with ratios if we knew H2. We don't know H2, so we actually don't know the vertical distance for T2. So we have to find another way to do this. And the way that we're going to have to do it is by drawing some kind of, I'll do it with green so you can see it. We have the cable like this, and we're going to draw a perfectly horizontal line over from B straight into cable that holds up C, or straight into the vertical of C. So then this angle here, this angle, we're going to label it as, this is going to be theta. Theta is this angle. So theta is going to be right here. This right here is this right here, because we took the cut, and so theta is the angle between T2 and a perfectly horizontal line. Excuse me, geez. So knowing that, we can do both some of the forces in the x and y, and then use that equation to derive our T2 and our H2. So let's start with some of the forces in the x. So the force in the x is going to be equal to 0. It's going to be equal to 1 over square root 2 times AB, which is known. And we're going to have, so this should be minus, because AB we know as tension is going to the left. And then we're also going to assume tension here, so we're going to say plus because it's moving to the right. This will be plus our T2 times, and since we want the x component, we're going to take cosine theta. Because T2 cosine theta is going to take this and turn it into this. It's going to give us the x component of the diagonal, since cosine is the adjacent side of the triangle. From our angle, the x component is the adjacent side. And that's it for the sum of the force in the x direction. So we have minus 1 over square root 2 AB, which is known here, plus T2 cosine theta. We're also going to have the y direction. And this is also going to be the same ratio here. 1 over square root 2 AB. This is going to be positive because knowing this is tension, it moves to the up. It moves up and to the left. Then we have minus W1, so minus 100. It goes straight down, so we don't need any kind of ratio. And then we'll have minus T2 sine theta. We use sine here because the opposite sine is opposite over hypotenuse. The opposite side from theta is going to be this vertical section here, giving us the vertical component of our T2. So if you change this algebraically, you move this T2 sine theta over by adding it, and then you combine these terms, and you move the 1 over square root 2 AB over by adding it, because this is the negative one. And we treat the T2s as though they're on the same side of the equations. We can rewrite this as T2 sine theta is equal to this 1 over square root 2 AB, AB is known, minus 100, comes out to be 33.3. And we can say this is divided by T2 cosine theta. And remember this from your algebra class, you can divide equations with other equations to cross off unknowns. Because once we do this, and this comes out to be 133, once we do this, our T2s are going to get crossed off because T2 sine theta divided by T2 sine theta is just going to give us tangent theta. Sine over cosine is tangent. This will come out to be a number, and therefore we can take the inverse tangent of this, and we can say that theta is equal to 14 degrees. So now we know our theta. We can go back to one of these equations. Let's say, we'll say we go back to the minus, or to the sum of the force in the x direction, where we have minus 1 over square root 2 AB, which is known, plus T2 cosine theta, which theta is now known. T2 is our only unknown. So we plug in 14 degrees for theta, we plug in 188.5 for AB, and we can say that T2 is equal to 137 pounds. We get a positive answer, so our assumed tension is correct. And once again, this just comes from plugging 14 into theta and plugging 188.5 in for AB. So now that we have found our T2, actually we found the second thing first, but the last thing it wants us to find, H2, we know is just going to be, we know that is just going to be, we know that if we take the theta that we found for this angle right here, and we use it and we say tangent 14 degrees is going to be equal to H, which is this. We're going to say that this right here is H. That's H. And that's going to be over 1. 1 we know is the x distance. And we're going to treat that as the same down here. So we're going to have h over 1 for opposite over adjacent. Therefore, h comes out to be, you do this just by doing tangent 14 times 1. H is going to come out to be 0.25. And since we found this distance, and we already know this distance, which is the rest of this, you can just add the 1 meter and our h value to get the entirety of h2. h2 is equal to the top all the way down to b plus the h value that we found, because h is from c up to b. So h2 is equal to 1 plus 0.25. So we can say that T2 is equal to 137, and we can say H2 equal to 1 plus 0.25, so 1.25 meters. Sorry, and this should be newtons, by the way. I just wrote pounds out of habit. Don't do that. Don't be like me. Write the correct units, which are newtons for this problem. All right, that's the second problem. So we can move on to the third problem. I gotta clear this. Okay, so now we've got problem number 4. These are pulleys. So for this one, we can see that it wants us to determine the magnitude of the force P needed to support the 100 Newton force in each system. Here, our 100 Newtons are right here. So that means this P is going to need to hold this. What we can do is we can trace our P. We can say, this is P, and wrap it all the way around to where it comes out to this side. Well, this is also P. And we just keep going. Oops. Just keep going. And boom. Now that's also P. This is going to keep going around this circle. We have another P. And around one more time up to the fixed support, and that's another P. So we have our first P on the side, and then 1, 2, 3, 4 P's in the cut. So when we cut this, and we say we just have this pulley right here with the 100, we're going to have P, 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 and P. All of these are P. So now that we have this, and we know that they're all P by doing the tracing that I showed here, we know that these are all P, we can say sum of the forces in the y direction equal to 0 is equal to P times 1, 2, 3, 4. We have 4 P's minus 100. You can easily solve this because this is the entire equation. For this free body diagram, we have P is going to be equal to 25 newtons. And that's the force P needed. That's it. We can look at this one as well. And we can see our 100 newtons here. And we can see our P right here. So we can do this one in the opposite direction. We can say, okay, so if we need 100 newtons here, we're going to need 100 newtons here, because this is equal to this. It goes around. And if we have 100 newtons here attached to the center of this pulley has 2 cables, one that goes like this and one that goes like that. They go around, they must be the same. And if you were to do some of the forces about this pulley, you would have 1 versus 1, 2. So these 2 must both be half of this one. So this has to be 50, and this has to be 50. Sorry, I should go ahead and write that this has to be 100. So this 50 goes into the support right here. Kind of like, we don't worry about this anymore. This 50 that continues on towards our P goes around all the way up to here. And this 50 loops around, so we know that this must be 50. And once again, we have the 50 connecting to the center, and then we have a new pulley that splits our force into 2. And if 50 goes into 2, this must be 25. And this must be 25. And that 25 loops around, and would you look at that, it meets our P. So P here must be equal to this. Once again, P is equal to 25 newtons. And you can do both of these problems simply by tracing your P or your force through the system and seeing where it goes. Now we have this problem, problem 14. Second to last one, we're almost there. Excuse me. So this problem, yeah, I'm gonna have this right here, just so I have the extra space just a bit. For this problem, this is gonna be a frame using a pulley, 2 pulleys technically, and a weight right here. We know that this weight, says in the problem, is 50 kilograms. So if that's 50 kilograms, we can multiply by 9.81 and know that this has a weight of 490.5 newtons. So that's, once again, that's just multiplying the mass, which is 50 kilograms, by 9.81, which is the gravitational constant. So this problem wants us to determine the horizontal and vertical components of the reactions at A and D. So we see that these are both pins. We're going to have an AX and an AY, a DY, and a DX. So for this one, it's going to be difficult to do moments for the entire diagram with what we're given, so we can go ahead and start pulling pins to break this up into smaller pieces. We can go ahead and start by pulling the pin at C and separating this into AC and DC. So let's draw our AC diagram, where we have a bar. We're going to have our AY and our AX. We also have this pulley, roughly in the center, exactly in the center technically here, roughly in the center on my drawing. And we have the outside pulley. So we know that we have 490 here as this weight in this cable, and we follow that cable around just like we did before until we get here. And if we're separating this member AC from the member DC, this cable is going to be cut, and we're going to have another 490. We know that this is a tension, so this must also be a tension moving away, like into the cut, away from the diagram. We cut this, we cut that, and we have a tension and a tension. We're also going to have a CY and a CX. So it's AY, AX, cy, cx. So we can start off by, and real quick, important to note that these 490s are not exactly lined up with B and C because of the radius of the pulleys. The pulley has a radius of 100 millimeters or 0.1 meters. So this 490 is actually 0.7 away from AY, away from A in general. And the 490 on the right is 0.1 meter away from C. So knowing that, our goal is to find the reactions at A and D. So we can go ahead and do a moment at C. I'm gonna write this different color. We can do a moment at C is equal to 0 is equal to, if we're going clockwise, we'll have a plus 490, and it's technically 490.5. I'm just writing 490 for the sake of it. It's times 0.1 meter. Cx and Cy are going to go away. Taking the moment clockwise, we're going to have minus 490 from this piece. That will be times 0.8 plus another 0.1, so times 0.9. AX will go away as it moves all the way through here, passing through C, and we'll have minus AY, since we assumed AY going down. Times the entire distance of 1.6 meters. And that's our entire moment equation for C, so we can go ahead and solve that and say AY equal to 245. And we get a negative answer for this. So we know that our assumed direction of down is incorrect. So it will actually be 245 newtons going up. This is the first piece of the answer we're looking for. Coming back to this, we're going to, before we can move on to DC, we're going to need to figure out some information about C so that we can solve for our unknowns on DC. We're going to do our sum of the forces in the y direction because AY is known. We have our two 490s and CY is our only unknown. We can go ahead and say that CY is going to be equal to the difference between 245 minus 490 minus 490, and it's going to be the difference we need to bring that back to 0. So we'll say that, and that's just found using your sum of force in the y direction equation. So we can know that once we solve this, that CY is also actually equal to sorry, 1 second. Oh, I was just reading it incorrectly. We've been doing it correct. Do not worry. So we know that CY is going to be equal to 735 newtons going up. That's what I get for not writing out the equation. I almost thought I messed it up, but no, we're good. So now that we have CY, we can go and write out DC as a bar like this, where we have dy, dx, right here, we're actually going to have this cable exerting a force like this to compensate the other side of this cut. This is also going to be 490. And then we move up to the end, we have Cx, and our known Cy as 735, except now that we're on the other side of the pin, our Cy is going to go down. So knowing this, taking a look, we can see in the y direction, we have two knowns, one unknown. So we can do some of the forces y direction. It's going to be equal to dy plus 490 minus 735. And that's it. We just say that dy, solving this, we say that dy is equal to 245 newtons going up. Second point that we're looking for. Next, we could do, now that dy is known, that's known. We only have two unknowns here. So if we were to do a moment about c, cx would go away, and dx would be our only unknown. So let's say we do counterclockwise moment about c is equal to 0. Is going to be equal to doing this equation, we're going to get the 735 to cross off. Cx is going to cross off. So we'll have plus 490 times the distance from C to this 490 is going to be 0.9 meters, just as it was before. So we go from here all the way out to here, which is 0.9 meters. We're going to have plus dy. Sorry, this 490 should be, oh wait, no, yeah, it's positive. It's positive. We're going to have plus dy as well, which is known. We just found it, times the full 1.6 meters. And then last, we're going to have minus dx, as dx contradicts our moment direction, as we have the moment labeled positive as clockwise, so dx is going to move against that. So we'll have minus dx times the distance from dx up to c. That's going to be 1.2 meters. You solve that out, and you can get dx is equal to 695 newtons to the right. Since we got a positive answer, our assumed direction to the right is correct. That's 3 down, 1 to go. Going back up, because we now know dy and dx, we can go back to our AC diagram. We already found ay. Our only unknown is ax, and we know based on this diagram that ax and cx must be the same because they're the only forces in the x direction here. And based on this diagram, we can see the same thing. Cx and dx are the only forces in the x direction, so they must be the same. So dx moving to the right, Cx is going to be 695 moving left, jumping back up to AC. Cx is going to be 695 moving right because the direction is going to change since we went to the other side of the pin. And then AX has to be equal and opposite. So AX will be equal to 695 going to the left. That is every piece that it asked us to solve for. And now finally, we have one more problem. We're going to clear all drawings. We have one more problem. Come on, mouse. There we go. And it's this one, problem 13. Now, this problem is going to involve tipping and slipping and belt friction. So this problem says block A has a mass of 50 kilograms. So once again, we know that this is 50. We multiply it by 9.81, and we know that this is 490.5 newtons going down. And it rests on surface B. Oh, I'm sorry. This is 50 kilograms. My bad. So right here, we have a weight of 490.5 for the large block. Surface B, which has a mu sub s of 0.25. So the mu sub s for surface B is 0.25. If the coefficient of static friction between the cord and fixed peg at C, here we have C, is 0.3. So our friction value here is 0.3. And our friction value here is 0.25. It wants us to determine the greatest mass that the suspended cylinder D can have without causing any impending motion. So we must assume tipping and then assume slipping, check our belt friction, and see what mass comes out. Excuse me, geez. So what we can do first is assume tipping. And what we're going to do for that is we're going to have our diagram here with the weight and a normal force, a friction, and our tension. So what's going to happen here is we have the normal force on the corner, because as soon as this thing starts to tip, all of the normal force will be here. There will be no friction along the bottom, and our normal force will be focused entirely at this corner. What we can do is take the moment about C to get the normal force and the friction to cross off. We can do, let's say, clockwise moment about C equal to 0. It's going to be equal to, this is our unknown tension, this is our weight. Here we have N and F and W. This is W. So this is going to be equal to minus our weight times the distance from the edge to the center. The weight is going to act in the center. We have 0.125. And then we'll have plus the x component of our tension. The y component of our tension is going to pass through the point that we're taking the moment. I should label this as C. The y component of our tension is going to pass through C and not be included in our moment equation. So moment about C, we're going to only have the x component, which will be T times the correct ratio of 4/5 given to us by the problem. And that's going to be times 0.3 meters. You can solve this for T, and you get that T is equal to 256 newtons. So we know that as soon as T hits 256, our system is going to be in equilibrium, and as soon as we go just over 256, like 0.0001 more than 256, it will tip over. So now we can move on and say we're going to assume slipping. For this, we have a diagram very similarly with our weight in the center. We're going to move our normal force to the center, and we're going to have our F along the bottom per usual, and we'll have our unknown T. So for this problem, it's a little, we have a little bit more to do than for the assumed tipping. What we're going to need to do is take some of the forces in the X and Y direction in order to get equations for T that involve N as well, and we're going to have to do a systems of equation. So what that's going to look like is we're going to have some of the forces X direction is equal to 0. It's going to be equal to minus T times 4/5 and plus F. However, we know that F is going to be equal to mu sub S times N. F is equal to mu sub S times N. So we can replace this and say minus 4/5 T plus 0.25 N, because we know that mu sub S for this surface is 0.25 equal to 0. And we know that if we do some of the forces in the Y direction, equal to 0, we're going to have plus 3/5 T minus 490 and plus N. So we can rewrite this as 3/5 T plus N is equal to 490. We can use both of these equations and substitute our values to find T. So T, once we do that, we'll know that T is equal to 129 newtons before it will slip. So comparing our T for slipping and our T for tipping, we can see that our T for slipping is much lower, meaning that our system will slip before it tips. Therefore, when we want to find out the maximum mass for this cylinder, we need to use the slipping force, the slipping tension force. So the last step for this is to do the belt friction portion. Since we are given a friction for the rope, we have the peg here, C, with our T value like this. We'll call this T1, and T2 going down. We have a different T on both sides because we're given the friction, the mu sub S for the point C, meaning that as this rope moves across the peg, the force in the rope is going to change. So what we know, or what we need to know, is T2. We already know T1, and the formula that we're going to need for this is that T2 is equal to T1 times E to the power of mu sub S for the peg, so that's mu sub S here, times beta. And what beta is going to be the angle from T2 to T1. Because T1 does not leave right here. It leaves down here. So we have slightly more distance than if this were a 90-degree angle. But that plays into the concept that we do know that this is a 90-degree angle from T1 to the perfect top of the peg C. We also know that this angle from T1 to a perfect horizontal, we can call it theta. And this angle from the 90 degrees to perpendicular of T1 is the same theta. These angles here are the same that I marked in purple. So what we can do, since we know we know the dimension of the rope, we know the ratio, the slope of it. We know that this is a 3-4-5 triangle. So what we can say is we can say tangent theta is equal to opposite over adjacent. Opposite is 3, adjacent is 4. So solving this inverse tangent of 3/4, we know that theta is 36.9 degrees. And taking this theta value, we add it to the 90 that we already had, and beta is equal to 126.9 degrees. Except we need beta in radians, so that's actually divided by 180 and multiplied by pi, 0.705 pi. And this value is what we need, the last thing we need for this equation. So now that we know T1, we know mu sub S, and we know beta, we can plug it all together and say that T2 comes out to be 251 newtons. Once again, that's by plugging in the smaller T value that we found by comparing our slipping versus our tipping. For T1, we plug in the given mu sub S is 0.3 for this surface, for our mu sub S here. And then beta is the angle from the perpendicular of T2 to the perpendicular of T1. Plugging that all together, you get T2 is 251 newtons. That was all the problems that we went over in the first exam review session. All of these problems are available in the exam review module on the Canvas page. There will be another exam review session for exam 2 on Tuesday from 1 to 4 in my usual Zoom link, and also in the Holmes Engineering Lounge if you wish to attend in person. If you have any questions about this or other problems, feel free to email me, and I can help the best I can. Thanks so much for for watching the video, and sorry for the inconvenience that I had to redo this.